Hey everyone, it's Max Sklar from the Local Maximum, and today I am thrilled to share that after a ton of work, I recently published a research paper on Arxiv. It's called Sampling Bias Correction for Supervised Machine Learning. A local link is available, as well as a Local Maximum podcast episode. That's episode 218. The paper says that if you receive only a portion of a data set for machine learning, and you know the mechanisms by which the original data was abridged, then you can work out the formulas for learning on the original data set. In other words, you try to find out the answer you originally wanted, not the one on the biased data set that you got. The lost data will make your results less certain, but at least the bias itself can be counteracted in a principled way. I originally wrote this because of a problem that I worked out when I was building and I was working on the attribution product for Foursquare back in 2017. We were using machine learning to predict the likelihood of people visiting places because the non-visit examples were humongous, because usually you don't visit a place. We sampled it at a larger rate than the visit examples, and the mathematics of sampling bias was researched to counteract this. I encourage anyone who is interested in machine learning and computer science in general to check out specifically the introduction, specifically the first couple pages. It's a very quick read, and it presents high-level ideas in our field. Section 3 also is really just Machine Learning 101, which I started writing it in order to establish the vocabulary, maybe get the variable names straight that I use later on, but eventually decided to make it a freestanding walkthrough of the machine learning process. So if you want an introduction to machine learning from a Bayesian perspective, read this section. It serves as a high-level primer for people who are unfamiliar with machine learning but have some mathematical background. Supervised machine learning is specifically what it's about. It's not the only variety. It's not always presented as a Bayesian inference problem either, but I think this way of looking at it, this way of presenting it, is an incredible tool for anyone who is trying to learn how all of this works. If you want to gain expertise in the bias correction problem specifically, and you want a deep understanding of how the Bayesian formulation solves this, then I think you should read the whole thing. Of course, if you just need to solve the bias correction problem for work, your deadline's coming up, feel free to just skip to the answer. It's in section 5 and section 6 for logistic regression, specifically if you're using logistic regression. I hope that this research demonstrates that formulating a machine learning problem in the language of Bayesian inference helps to break down and answer really tough questions. This particular solution would not have been possible without thinking in terms of Bayesian distributions, and I think that this paper will serve as an excellent case study for people to understand why that is. So I think once you stop thinking in terms of exact answers and you start thinking in terms of beliefs over possible answers, a whole new world of insights opens up. Finally, I really want this to be used in practice. Much noise has been made about bias in data sets. The solution I present here will allow practitioners to perhaps make assumptions about the bias and peek at the consequences of those assumptions, which is a useful first step. But more immediately, it's the original motivation of the paper, which is to reduce the size and composition of training sets so that computation becomes more efficient. The thinking behind this, it kind of progresses in 4 steps. The first step is you have a big data product. Great news, we've got a ton of data to run this model on. We can build something useful here. Second step, there's a drawback to big data. Hey, using all this data takes a ton of resources. Are we past the point of diminishing returns? In other words, is the right amount of data the exact amount of data that we have, or would it be better if we had more data, or better if we had less data? It's probably not the exact amount of data that we have. So how about we throw out some data, maybe pocket the savings, and the result will be just as good, or like 95% as good, which is totally fine for us. Third step is, okay, so I want to use uniform random sampling for this. How many examples do we have? Let's say we have 100 million examples, huge data set. I think that if we train on only 1 million, then we'll still get good results. So that we don't have to transmit all that information. That's a lot of savings. So for each data point, I'm just going to pick a random number so that it chooses to keep it. It chooses to accept it 1% of the time. Then we'll end up with around 1 million points. And then finally, you get to bias sampling. It's like, but wait, some data points are more valuable than others because we have a label imbalance maybe, or maybe some other reason. So let's be more selective about what we throw away. This means we can either safely throw away more data, or we can get better performance from that 1% rate that we did before. Now that bias sampling can be dealt with appropriately, this method can be deployed routinely and hopefully bring about compounding savings in any machine learning and system and data pipeline. A little bit of work still needs to be done, or actually quite a bit of work still needs to be done in terms of solving for specific cases, as this paper does for logistic regression, which is very common. But there are a lot of other specific cases out there. The paper gives you the general case, the general solution for bias correction for supervised machine learning for a certain general sampling type. But I think a lot of work needs to be done in kind of crystallizing what those means for specific types of machine learning, and also accounting for some different sampling types that I put in the future work section. So let me know if you're interested in any of those questions. I'll give you my assessment. Finally, this exercise made me come to understand that the teaching of Bayesian inference, while it's fairly standardized, is still ripe for innovation from educators and from systematizers. For example, if you look at the mathematics of Bayes' rule, it benefits from considering probability to be proportional rather than absolute. In other words, how is it, maybe A is twice as likely as B, rather than, there's a 0.06% chance of A specifically, which is more absolute. So this allows us to safely remove all those pesky constant factors, which are ultimately unnecessary when you work out the Bayesian math. And also it confuses the hell out of everyone trying to follow the math. So I tried to rely more on proportionalities and the idea of probability ratios rather than raw probabilities, but I'd like to see better notation around it. For example, in a proportionality statement, it should be, I use kind of that squiggly line, it should be a little more obvious which symbols are considered variable and which are considered constant, and make it a lot easier to manipulate. So yeah, that's one takeaway. I hope to continue this line of research and incorporate these tools into my future projects, including newmap.ai, which is an exciting new thing that I'm currently developing. More on that soon. Yeah, hope you enjoy this piece of research, and I hope a few people out there finds it interesting enough to read and find it useful. So have a good day.